Thanks, Lisa. Thanks, everyone. Thanks to the organizing team for putting together this fantastic conference. I'm sorry I wasn't able to be there in person, but I'm thankful for the opportunity to be able to present this work on the value of improved electricity reliability. Let me do this. Sorry. Yeah. Okay. On the value of improved electricity reliability for firms and households using evidence from Senegal. My name is Abdoulaye Cisse. I'm a fifth-year student from UC Berkeley in the US. So by way of motivation, I'm starting with the observation well known to most of us that electricity reliability is a major constraint for both firms and households, generally in low-income countries. And this is apparent in the typical data set that we are familiar with, such as the World Bank Enterprise Surveys, where a lot of firms report electricity as being a major constraint, as well as on the household side when you look at surveys such as the Afrobarometer. At the same time, utility companies around the world are making large capital investments to upgrade their grid infrastructure. And the reason for these upgrades can be many. For some, it's to improve reliability, such as the context that we're looking at. For others, it's to adapt the grid to upcoming challenges to electricity access, electricity generation, electricity distribution. And these capital investments are projected to rise significantly in the coming years and decades. With that said, it's important to understand the value of these large grid upgrades for consumers broadly defined. And so that's the point that we are trying to focus on in this project by asking the research question that is hopefully relatively simple but interesting, which is trying to get to the value of improved electricity reliability for both households and firms. And so we are going to do this using a large-scale or studying a large-scale natural experiment that targeted reliability improvement in Senegal. And the design here is going to be that of event study, where we are going to use the timing of the rollout of this project, which I will give you more detail about in a few slides. And so we study this using a rich set of disaggregated data that combine high-frequency outage data from the utility, along with disaggregated client-level bills for customers, both firms and households, as well as geocoded panel surveys of consumers that give us a rich set of economic outcomes beyond electricity that we can study. And so in terms of empirical analysis and reduced from result, we find that the reliability improvement project do lead to fewer outages as is expected. And so this turns into higher electricity consumption for consumers, as well as high appliance adoption. When we zoom in on firms, we find that the reliability improvement project result in higher firm survival rate or low firm exit rate, and more new family-owned enterprises or more new businesses coming in place. We also see higher self-employment, so in line with new businesses, and we see suggestive evidence on more productive use of household time. So that's kind of the empirical analysis, and I think that's going to be most of the slide for today. We connect these results to a demand model in order to be able to derive a marginal willingness to pay for reliability, so tying the empirical analysis back to the question on the value of these projects. In terms of the literature, briefly, I'm sure most of you know very well the paper that I cite here and the literature broadly. I just wanted to highlight maybe two papers here. The first one is the Mensa 2024 one, which came out this year, JDE, and there is a nice VoxDev article. So it's this fascinating article that study job creation in the context of electricity reliability in sub-Saharan Africa. We have the second one, Berkau and al. That study grid updates in Ghana. And Mix and al. Study reliability improvement, mostly focusing on voltage fluctuations in Kyrgyzstan. And I'm highlighting these three papers to say that there is a literature that's already looking at the impact of reliability on firms and households. And so here, the contribution point would be to zoom in on persistent and large changes in outages that are coming from large-scale system upgrades. So here the focus is going to be on these large-scale system upgrades that are going to kind of cover most, if not all, of the electricity network. And so what this gives us is a long-term, an opportunity to study long-term impact of persistent and large changes. So that's really the main point, at least of the empirical analysis. And then we touch on these other pieces of the literature that I'll skip for in the interest of time, but happy to come back to. In terms of the context, just briefly, we are studying here the electricity market in Senegal, where we have one state-owned electricity provider called Senelec, which has about 2 million customers between firms, residential clients, and commercial clients. And Senelec is partially in charge of production, meaning it gets some of its production from other entities through IPPs, but otherwise is fully in charge of transportation and distribution from power generation to downstream consumers. In terms of the current state of things, in terms of outages, clients get on average 20 hours of outage per month. This is about 10 times outages that last 2 hours. And these outages can be of two types. They can be either planned, where the utility knows ahead of time that they're going to turn off electricity, and it's mostly to do maintenance work or to test lines or to do some load shedding when there is some capacity constraint or some production constraints. We also have unplanned outages, which are related to any incident that happened on the line that is unforeseen by the utility. And we have about 80% of unplanned outages and 20% of planned outages in general. This map, or this stylized schema, just shows a simple version of the electricity distribution network, kind of zooming in now on the part that I'm studying. So we have the upstream part, which is related to the generation and transmission lines. And so that's where electricity gets generated somewhere and is transported through a high voltage line. That's not the part that we are studying here. Instead, we are focusing on the downstream distribution network, where once the electricity gets generated, it gets to this what they call source stations that I'm calling here source A and source B, then get fed into feeder lines that serve distribution stations or transformer stations, which then gets to households and firms that are the end consumers. So here, the project that I'm studying are really at the station level or at the transformer, at the distribution station level. And so the project that I'm studying are of two types. One is going to be installation of remote control switches on the lines. And this will allow the utility to essentially be able to isolate faults online, but doing so remotely. So gaining time on isolating faults remotely, as opposed to having to send someone on the ground, which obviously may take time depending on how far it is and how complicated the issue is. We also have another type, which is related to the installation of smart meters on distribution station. And this, again, is going to give the utility electricity data related to voltage current readings in near real time, which will allow the utility to prevent and detect these outages, again, remotely and be able to gain time. So, yes? Okay. So the goal of this is to be able to reduce the pass-through of outages across the network and turn what they call global outages, which would be outages that feed through the network, so that may have a starting point, but quickly feed through the network, and turn it into local outages that are contained within a given local part of the network. So in a way to reduce the damages and be able to locate where the issue is quite fast. So now moving on to the empirical analysis. The data that we use is going to be a few pieces that all relate to electricity or economic outcomes. So the first one is going to be the universe of outage incidents for all distribution stations for over 8 years from the utility company. So these are going to be logs of incidents that will give information on the nature of the incident, the cause, the location, the duration, and things like that. We put this together with detailed maps of electricity distribution networks. So these maps are very rich in terms of being able to give us all the information on what is exactly on the networks in terms of devices, line, how they're structured, what are the sequences of the station. So essentially, we are going to track the events that we study from these detailed maps, and they cover about the same period at the outage incidents. We also have a universe of electricity bills for the 2 million customers that I mentioned earlier for actually a longer period of time, which is really nice because this is clean. It allows us to observe all clients in the country for a quite long period of time, and we can map this to the other data set, and so be able to do a long time horizon study. We also have a geocoded panel of household survey with a much smaller sample, but still quite meaningful of 7,000 households or so. It's more recent, 2018, 2019, and 2021, 2022. The nice thing about this panel of household survey is that it covers a lot more variables than electricity, which are what the three first data set are about. And so we are going to leverage this fourth piece of data quite heavily. And we also bring in some satellite data because all of these data sets are geocoded, which will give us some coverage that we are also going to include. So yeah, we match all of this based on geocoding, and I'm happy to come back to that if it's relevant or yeah, interesting. So this is just a map. Yes.
Can you say how do you measure well index through satellite data?
Yeah. So yeah, good question. So the satellite data, I don't really put any of this together. I just grab it off the shelf. So the wealth index is the relative wealth index that Joshua Blumenstock from Berkeley here and his team have put together for it's a cross-sectional data, so not really panel, but it's geocoded based on I think ground truth survey data that they use to test the model. Okay. So yeah, just moving on. This is just a map showing the map of Senegal with in gray the build. So these are the customers with build. Obviously, we would have many customers within the same neighborhood. So maybe stacked points, if you may. And we have in black the household survey, so the geocoded household survey that I mentioned, which are much fewer in terms of number of points. And we have the stations in red, which are the transformer station that the utility, that the electricity passes through to go to customers. This is just a time series showing the timing of the rollout of the reliability improvement project over time. So started quite slowly in 2015, and then by 2023, a lot of the stations were treated. So maybe just briefly, in blue here, we have the total number of stations in the network. So this is just how many distribution stations are in the network, and we see that the number is increasing, and that relates mostly to access, actually. So over time, the utility company is building more stations, trying to get to this last mile connection issues into more rural areas, and that's what's translated into the increased blue line in blue. In orange, we have, in red, sorry, we have the stations that are actually treated with the devices that I mentioned earlier. So in number, it's about 1,000, but these stations are obviously in part of feeder line that they share with other stations. So in orange, I'm showing stations that share feeder line with any treated station. So that share feeder line with any station that is in the red line, that is part of the red line. And so just briefly, in terms of what determined the timing of the reliability improvement project, it was not random, but luckily for us, we have some information on what information the utility used as criteria. And it's essentially, I think none of this is really surprising. It's going to be the utility trying to maximize the return, so to speak, of these devices. So if the station has a lot of sublines, that is a station that is going to serve a lot of customers, so they will prioritize that. If the station is far from where the utility is located, meaning the time needed to send a technician to the station would be quite high, then they will prioritize that. The density of the number of clients that is served by station, so population density, is going to be kind of related to that first point on the number of people that are served. And then critically, you have the level of importance of the station. So if If the station is serving a critical infrastructure, then that's going to be prioritized over stations that are just serving regular firms and regular clients. And they have 5 levels of importance that are from urgent to strategic to critical to important to standard. So luckily for us, we have information on this variable. So what we are going to do is first check that they correlate with the timing of the reliability improvement project, which they do, and then we are going to use them as control to try to kind of assure some of the concerns about the endogenous timing of this reliability improvement project.
I have a question. If I shout it, can you hear it from here?
Yes, I think so, yeah.
It's not working.
So this will go.
So anyway, can you hear me?
I can hear you, I think, yeah. Go ahead.
Okay, 2 clarification questions. So just to confirm, so you're doing this at the distribution substation. So is that 66 kV, the capacity of the substations? Okay, maybe I should get a mic.
Are you saying the capacity is fixed at the distribution station?
So maybe this is better, hopefully. Okay, yeah, I can see the reaction. Right. Okay, so 2 clarifications. One was, this is the distribution substation, is that right? So 66 kV that you're looking at the intervention. And then the second one was on how you mapped the customer data to the substations. Was that in the billing itself that you know which substation is fed? It feeds a particular customer, or do you do that just kind of by proximity?
Yeah, question there. So the answer to the first question is yes. I'm looking at. I'm always struggling with what is the right name to call this. I'm calling them distribution station because that's what the utility is calling them. But I think a substation, 60 kV would be maybe more more standard. On the second question, what I'm is also a great question. What I'm doing here is I don't have the direct mapping between customers and the distribution stations, meaning for any one customer, the utility doesn't tell me that they belong to station A. Most stations here, at least in my context, are given the names of where they are. And I have the addresses, the literal addresses of customers, which I geocode. So what I do is I use the literal addresses as well as the geocoded address to see whether the station that the geocoded the geocoordinate say is closest to the customer is close in name to the stations. I'm not sure if what I'm saying or how I'm saying it makes sense, but essentially some fuzzy matching, some very conservative fuzzy matching, out of which I throw away all the customers that I cannot guarantee with a high degree of certainty that they are treated by the station that I assign them to. Okay, yeah, happy to come back to this if there is time. Yeah, this is just a slide showing that I'm running an event study design, kind of building off of what the timing of this reliability improvement project over time. So here the project dummy is the year in which the station received a reliability improvement project. So the treatment is at the station level. We have this cover that I mentioned before, and we are clustering things at the district level. So the identifying assumption here would be that if we didn't have this reliability improvement project, the outages in sites that were treated early would trend similarly relative to outages in sites that were treated late, but are in the same district. So trying to keep here the analysis at the within district to be a within district analysis. So here we have the first result on the impact of this reliability improvement projects on outages. So this is just kind of step 0. So on the left we have the duration of outages 5 years before a station receives a reliability improvement project and 3 years after. And we show on the y-axis the total hours of outages in the months in blue before and in green after, and we see a decrease of about 5 to 10 hours of outages after the reliability improvement project come in. On the right, we have the frequency of outages. I want to show it just to show that the mechanism, as I explained, was that it was going to reduce duration. Although it's a network where everything communicates, it doesn't directly target frequency of outages. So what we see here is that you could read about the levels before and after, and maybe see some insignificant decrease in the level of the frequency of outages in terms of number of outages, but it's not significant. So most of I guess the main mechanism is going to be the reduction in the duration of outage. And so this second set of regression looks at the impact of the reliability improvement project on electricity consumption. So on the left, I'm showing electricity use in terms of kilowatt hour. This is at the build level. Yeah, I should mention that. So this first event study is at the station level. The second event study result is at the customer level. So it's a bit more granular and perhaps a bit nicer and less noisy. And so on the left-hand side, I'm just showing kilowatt hour in terms of electricity use. Again, some years before and some years after. On the right, I'm showing electricity expenditure, some years before and some years after. And what we see is about 5 to 10% increase in electricity use and electricity expenditure post the reliability improvement project. So it seems to be the case that the decrease in duration did lead to an increase in electricity consumption. So this is kind of in line with some of the work. Roy and Kana have a paper looking at the elasticity of consumption with respect to reliability in India. And I think the magnitude that I'm finding here is in line with what they have. Next, I'm turning to...
Sorry, a question on the electricity use. Would you say the effect is mechanical from just the fridge is plugged in and then it just continues to consume energy? So basically based on baseline average electricity use and the decreased number of outages, could you predict this effect? Or is there an extra, I don't know, I'm buying a new fridge, I'm buying a new television?
Yeah, great question. Yeah, and yeah, it's something that this graph doesn't clarify. So yeah, it's great that you ask. So yeah, I haven't done that prediction. I need to do it. What I'm going to show, hopefully I have time for it, is some movement on appliance, which suggests that yes, there may be that mechanical effect, but there may also be something more than that. But it would be nice, I agree with you, it would be nice to kind of decompose that, disentangle the mechanical from the additional effect. I suspect that the mechanical effect will be there, but the suggestive evidence that I'm going to show seems to suggest that there is also something more. But I need to do a bit more work here for sure. Thanks. On the right, I'm showing. Oh yes, next one. Yeah. So just on the firm side, on the left-hand side, I'm again using the build.
Sorry, can I just ask a clarification question on this one? I was trying to ask it when you had the data slide up, but my microphone didn't work. So let's try again. On the next one, sorry. What's the firm data what type of firms are you referring to? I think in your data slide, you had household variables and household survey data and satellite data. But so this is from information on firms from household survey data, or you have other firm data?
Yeah, good question. Yeah, I guess, I should be clear on what I'm calling firm here. So yeah, this is from the builds, and it's essentially what they call the residential clients on the build, which are, in my case, going to be mostly micro enterprises, if you may. So yeah, a few large firms, like firms in the typical sense, I guess, but also a lot of small shops and small enterprises in general. But it's going to be sorry, not residential, commercial. I meant commercial, yeah. So
so we shouldn't think of this as sort of large scale manufacturing and so on. This is about micro enterprise, really.
Yeah, absolutely.
Okay.
I think we may have about 100 or so out of the 2 million, 100 or so, or 150 large manufacturing. The rest are just small micro enterprises. So yeah, that's most of the commercial will be that. So when I say firm here, it's mostly those people. Yeah, thanks for clarifying. So the survival rate here is going to be for the commercial clients, and what we do here is just seeing whether they keep getting bills. So for year T, do commercial client that got a bill in year T -1 get a bill in that year T, and that's what we reflect on that y-axis that we call the firm survival rate, and we see an increased reliability improvement project of some 10 to 15 percentage point, which is quite meaningful if you put it from a baseline of about 75%, which is quite meaningful if you put it against some of the literature that has looked at exit rate and firm survival rate, especially for the smaller enterprises. On the right-hand side, so coming back to the data question.
Question.
Yeah.
Hello. Hi. I don't know if you hear me. Okay. I was just wondering. So you say, so you're measuring firm survival using billing. How well can you track firms using their billing number? So if like a firm moved location, are they going to change their billing? Like, are they going to change their account number? And would that,
Yeah.
I don't know, affect your ability to track them? Or are you able to track, like, do firms have unique numbers that would follow them even if they moved?
Good question. Yeah, good question. The bills. There is an ID number, but it's tied to an account, not not a person or not a business. So to your point, if someone moves or if there is something that happened to the account, the account number may change, even though it's the same person. Luckily for us, we have information. The individual, we have their phone number. So we have this additional identifier that allow us to rule out some of these. At least I'm not sure, I cannot say with certainty that I can rule out all of them, but at least some of them we can for sure rule out, such as the one that you mentioned, where is someone like me, the firm, moving from location A to location B. Yeah. Okay, perfect. And then the right-hand side one is just showing non-ag, I should say non-ag, not non-family. So non-ag enterprises is coming from going back to the data question earlier about which data set. So the right-hand side one is actually using the household survey, so not the bills. So that's part of why it's much noisier. But I just wanted to show it to show that there may be some movement on non-ag enterprises for on the side of the household as well. So coming back to that question about whether the effect was mechanical, I want to present this mostly as suggestive evidence. Again, because it's coming from the household surveys, which are noisier and a bit harder to link to the rest. But what I'm doing here is I'm constructing a time series of appliance purchases from the household survey. And so constructing the event study based on that. On the on the y-axis here, I'm showing the number of appliances. On the left-hand side, electrical. On the right, non-electrical assets. And just showing that, at least on the electrical appliances, which are going to be TV, phone, fridge, fans, things like that, there may be some movement, although you cannot rule out that the levels are necessarily not the same before and after, but this is just mostly suggestive evidence regarding the mechanical effect. And so just finally, a last slide on outcomes beyond appliance and beyond consumption. So here again, I'm going to the household panel data. So the number of observations is about 5,000 or so for each. And each line here is a regression, is a separate regression where I'm regressing the outcome variable on that first column. I'm regressing it with a dummy for the reliability improvement projects, along with the usual fixed effect on time and locations, and then the clustering as before. And so what we see here is that on the outages, we replicate the result from the event study, although this data is different and much smaller. What I wanted to show here is on expenditure, employment, and time use. So on expenditure, we see this is all obviously more suggested than before, but there may be some movement on perishable goods that may increase in terms of how much the household spend on this, and no significant effect on non-perishable good. So if you put these two together, it would mean that total food consumption for the household would increase, but mostly coming from perishable. I'm kind of showing them separately. On the employment side, also I'm showing self-employment and employment by other firms or other enterprises. And so the movement seems to be coming from self-employment, which is in line with the non-ag enterprise result that I showed a few slides ago, and no significant effect on employment by others, which again, if you the Mensa paper that I mentioned earlier, this would be very much in line with that. In terms of time use, this is just to see whether there is any movement on time use. So here I'm showing daily hours, or how many hours in a day the respondents spend on household chores and on child and elderly care, and there seems to be some decrease on both of these. I obviously have to link this to the appliance results in order to make sense of it and see which appliances and what time of the day this do happen. There is a data set that I didn't mention, which is on which is on hourly use of electricity. It's covered a much smaller time period, which is why I didn't mention in the data slide, but it's nice because it's a 10-minute reading of electricity use. So what it could allow me to do is see whether there is more movement around midday versus late at night versus morning, things like that. I don't have that yet. So maybe I can.
Hi, Abdoulaye, just to say you have 1 minute left.
Oh, perfect. Okay, I was debating whether I should skip this. So maybe I can skip this, and just this is just to take stock of pretty much what we've discussed. So just to say that I want to link this to a model because I want to get to willingness to pay. Why? Because these reduced form estimates do not cover all potential impacts of reliability. So as much as I'm trying hard to show evidence that there is something there, it's not comprehensive. So what I'm doing right now, which I don't have any slide for, is to develop a dynamic model of appliance upgrades and appliance use. And so the goal here is to be able to estimate marginal benefit of electricity availability and marginal cost of using or purchasing these appliances. And so we will be combining the reduced form result that would allow us to identify the marginal benefit. And we need to basically identify the electricity demand curve. And we have some contextual details that may allow us to do that we're currently working on. So that's it. Yeah, thank you very much. Sorry, I wasn't able to be there again. And thanks for all the great questions and the comments as well.